Last time we finished our discussion of regular expressions with the idea that regular expressions, NFAs, and DFAs all describe the same category of computations or languages. So remember way back at the beginning we said that the whole point of this class is to study what computations are possible. And we drew this picture that looked like this. Well, not really a picture, sort of a diagram. It had this big box, and we labeled it all. And it was the power set of sigma star. That is, it was all possible sets of strings, i.e. all possible computations. And we mentioned that way down in the corner there's this really small part called fin that was only the finite sets of languages. Now the question is, how do the regular languages relate to this? We recall that the DFAs are the same as the NFAs, which are the same as the regular expressions, which is all just another name for what we call the regular languages. Regular languages, or reg. Okay, so now, what's the relationship between all, fin, and reg? Well, here are some things that we definitely know. We definitely know that reg is a subset of all. Why do we know that? We know that because all is, by definition, all possible subsets. Reg is some subset, therefore it must be inside of it. So that's kind of trivial. We also know that fin is a subset of reg because we previously demonstrated that it was possible to turn any finite set into a regular language with a DFA. Okay, so we know those things. We know that reg is bigger than fin, and we know that it's part of all. The question, though, is it actually the same thing as all? So, is reg equal to all? What would it mean if it were equal to all? What it would mean is that all possible computations can be written down as DFAs. So that means that any problem that you could ever imagine caring about solving, that could be written as a regular expression. That kind of, you should think that this is suspicious because, for one thing, remember how we talked in an earlier class about how DFAs always run in linear time? And you presumably know that there are algorithms that don't run in linear time, like sorting algorithms, which at their best run in n log n time. So either those are not algorithms, or something weird is going on. But that just tells you that we're not sure. That's not really a proof, because how do you know that sorting algorithms really run in that sense? In the context of this class, we don't yet have enough information to determine whether or not reg is equal to all or not. Well, I'm going to tell you that it's not equal. So they're not equal. So what is actually the case is that reg is inside of here. So I'm gonna tell you that, and we've got to actually prove it. So to prove it, what that means is that outside of here, there's some language that is definitely a real language. It's definitely a real subset of the set of possible strings, but it's not a regular language. In other words, fin, it includes things like 0, and reg includes things like 0 star, actually let's just say 0, 1, and 1 star. But there's something outside here in all that's not inside of reg. Okay, what would such a thing be? And how would we know? Well, let's just call this thing out here x. So what I'm claiming is that there exists an x that is inside of all, but there does not exist, but for all D inside of the diaphase, the language of D is not equal to X. By telling you that X exists, that's what I'm claiming. Now, think for a moment about how you could possibly prove this. To prove an exists, what you need to do is you need to give a concrete example, a witness, of the value that has this property. So I could tell you what it is, okay? And I know what it is. What it is we write it down as 0 to the n, 1 to the n. What that language means is an equal number of zeros to ones. And this is very different from 0 star 1 star, because 0 star 1 star means any number of zeros followed by any number of ones. So for instance, that would be like 3 zeros and then 5 ones. But 0 to the n, 1 to the n means exactly 3 zeros and then exactly 3 ones. Whatever number there are, there is an equal number of them. Okay, so this exists. I just have to give the example. But then I have to prove for all diaphase, the language of that diaphragm is not that. Now, how could you possibly do that? How could you prove that for every single DFA, its language isn't this one? We know that there are an infinite number of DFAs because there are an infinite number of those graph pictures. We could have more and more different graphs. So how could we actually prove this? It's very difficult to prove things about for all statements like this unless we have some way of doing something like induction over the set that we're talking about. So when you do induction, you prove something about 0, and then you say that if you know that thing about 0, then you can prove it about thing 1 more. Let me write this down. So the principle of induction, the principle of natural number induction says that if you prove p of 0, some property of 0, and then you prove that for all n, p of n implies p of n plus 1, then that proves for all n p of n. Because that's the principle of induction. And so this allows us to prove a for all. We can prove the for all on numbers by first proving it on 0 and then proving this inductive step. So is it possible to do something like induction on the DFAs? Can we prove something about small DFAs and then from that prove something about big DFAs? It seems not obvious how we could do that. It turns out that proving this requires us to think about things slightly differently. Well, maybe not slightly differently, maybe big differently. The big principle that we need to realize is sometimes to prove something about an infinite set, what you want to do, like our goal is to prove that something is not in an infinite set. In particular, we want to prove that 0 to the n, 1 to the n is not inside of the regular languages. That's our goal. Okay. So that's what our goal is. So if we want to prove that something is not in an infinite set, then one strategy is to do the following. First, prove that all things in the set have some property. For example, you might prove that, all humans are mammals. Okay, so that would be an example of, so we have a set of all humans, and we're going to prove that they're all mammals. Then what we do next, prove that the thing doesn't have that property. So for instance, suppose I were curious about whether my phone right here were a human, okay? Well, I could first prove that all humans are mammals. Then I could prove that this phone right here is not a mammal. And if I prove that, then I would know that my phone wasn't a human, okay? If there was any doubt about that. Okay, so then we conclude that thing is not in set. So if we were to write this out, that means that step 1 is prove for all A inside of reg, P of A. Step 2, prove not P of X. And then we conclude that X must not be inside of reg. Okay? Let me push this up, and we conclude that it must not be inside of reg. Of course, there's a step 0, which is what is P. Okay? So this right here is the process that we are going to go through. We're going to discuss what property is true of all regular languages. Then we're actually going to prove that. Then we're going to show that a particular language doesn't have that property. And if we know that it really is a language and it doesn't have that property, then that means that it must not be a regular language. So that's the goal. Okay. This property is called the pumping lemma. Sorry, the pumping property. It's called the pumping property. Typically, it's called the regular pumping property. And this proof right here, that everything has it, is called the pumping lemma. You may have heard these terms before, or you may hear them in the future. This is what they're referring to. Pumping property and the pumping lemma. All right, so let's do it. Let's think about what is true about all regular languages. So one thing that we know that is true about all regular languages is that there's some DFA that accepts them. That's kind of what it means to be a regular language. Okay. Then among all the possible DFAs that accept them, there's some that's smallest. And there's one that's the smallest. And there's one smallest DFA. Because recall that there can be DFAs that, are like long and weird. You know what I mean? Okay. So, as a little example, imagine that I told you that the string 0111 was inside of some language A. So you know that. We could ask the question, what's the smallest DFA that could possibly accept that string? And clearly the smallest one would be this, that just accepts everything. Okay? So that'd be the smallest thing that accepts this. But I haven't told you what A is. All I've just told you is that this thing is accepted. Let's ask kind of another question. Let's ask the question, what's the biggest DFA that, actually, this is the right way to say this. No, what's the biggest one? Let's imagine, that we have a DFA that's going to accept 011, and we would like that DFA to visit as many states as possible. Why do we want to do this? I don't know. We just want to do this. What's an example of a DFA that would still accept 011, but it would visit the largest number of states possible? Well, it would start off in some state, then it would see a 0, then it would see a 1, then it would see another 1, and then at that point it has to accept because it's going to accept this thing. So notice that this right here is like the smallest thing that could accept it, and this is somehow like the biggest thing that could accept it. It's not really literally the biggest because there could be other states that like we didn't actually like go visit. But the thing is that no matter what happens, if the input is 0, 1, 1, it's never possible to visit more than 4 states. The one we start in plus 1 for each one of the other states. Okay. So, what does that mean? That means that every DFA has some number of states. Some number of states. Just as an example, let's just suppose that it has 4 states. Say 4. Okay, so if it has 4 states, then what does that tell you? So suppose that the DFA accepts a string of length 4. So the machine has 4 states, and it accepts a string of length 4. What does that tell you? Well, let's look at this example right here. Suppose that it accepts a string of length 4, particularly let's suppose it accepts 0, 1, 1, 0. Well, we know that it's going to start here, that's state number 1, go to here, state number 2, go to here, state number 3, go to here, state number 4, but then there's still one more character, 0 there. So that means that this right here has to go to either this state, this state, this state, or that state. It has to go to one of the ones from before because otherwise there would be no place for it to go and there's only 4 states. So what this tells us is that all DFAs have loops in them. And the reason why they all have loops in them is because the delta function has to be total. It takes in a state and a character and has to go to some other state. There's no way for it to go nowhere. And since it can't go nowhere, that means it has to go somewhere. Now, some loops are boring. Some loops are boring. For example, we could accept the empty string and then go to a state and then loop there on everything else. That's an example of a boring state. By boring, I mean once you reach them, everything is rejected. Okay? And it turns out that all finite languages have boring loops. And it makes sense why this would be, because by definition, if the language is finite, then that means that it has to say yes to a finite number of things. But if there's a loop, and that loop isn't boring, i.e. if it isn't boring, what does it mean? An exciting loop has a way to accept. So if we were to draw a picture of it, that means that we would start, we would go to a bunch of stuff, we would get to a state, we would have a loop, and then there would also be a way to get to an accepting state. This is an exciting loop. And if your language has an exciting loop in it, then that means that there are an infinite number of strings because we could take this path and then go to the end. We could take this path and then go in the loop a few times and then go to the end. And there could be many, many times that we would go to the end. And so, since the existence of an exciting loop means that you're not finite, if you're finite, that means that you only have boring loops. Now here's the thing that's really interesting. Because all regular languages have a DFA, and all DFAs that accept infinitely many strings have exciting loops. Then that means that all regular languages all regular languages that, let me erase. That are infinite have the same kind of infinitely many strings. Okay? Namely, that they have ones that have this same loopy pattern to them. Now, what exactly is that loopy pattern? That loopy pattern is that you start in the start state, and then you have a bunch of transitions. And let's label them all X. Let's label the path of them X. And then you eventually get to a state that we'll call QR, R for repeated, the state that gets repeated. And then that QR has some path through the machine back to itself, and then some path that goes to an accepting state that we'll call QF, and we'll label it Z. I forget that I can erase, so let's make that beautiful. So QF, boom. Okay, and it is accepting. Okay, so what does this mean? This means that if X, Y, Z is inside of this language A, then that means that XZ is inside of the language, and XYYZ is inside of the language, and XYYYZ is inside of the language, and so on. There's in fact infinitely many of things that are inside of there. Each one corresponding to a different number of times we go around this loop. This property right here is the regular pumping property. It's the property that is in common with all regular languages. And every DFA that we've written so far has this property. So let's look at some boring examples. Well, maybe not too boring. Okay, so let's look at the ends in 0, i.e. even number. So that machine looked like this. We started in an accepting state, it looped on a 0, it went over here on a 1, looped on a 1, went over there on a 0. Okay? Well, X in this case is epsilon because we start in the repeated state, Y is 0, and Z is epsilon. So because X, Y, Z is in the machine, then we know that that any number of Y's is in the machine too. Let's look at something like the third from the end is 1 machine. Do I want to just like derive it again? I know what I can do. I'm going to look at the notes and go back to that page. Well, maybe this is a bad idea. All right. I'm almost there. All right, here we go. Okay, so it looked like this. So there was the blank. It had a loop on 0. If it saw a 1, it went down to 0, 0, 1. If there was a 1, it went down to 0, 1, 1. If there was a 1, it went down to 1, 1, 1. And then that was accepting. And then there was a loop here on 1. And then if there was a 0, we went to 1, 1, 0, which was accepting. If there was a 0, we went there. If there was a 1, we went up to 1, 0, 1, 1. And if there was a 1, we went there. And if there was a 0, we went to 1, 0. And if there was a 1, we went back. If there was a 0, we went there. And if there was a 0, we went to here, 1, 0, 0, which was accepting. And if there was a 0, we went back there. And if there was a 1, we went back there. And I think that covers everything. Okay. Getting back to, okay. All right. Okay, so this machine right here, what is an interesting loop that's in it? Well, the thing is that interesting loops, they just have to do with particular input strings. So what if we saw the string 0, 0, and then 1, and then 0, 1, 0, and then 1, 1, 0. Okay, so that right there. So notice that what this does is it goes 0, 0, 1, 0, 1, 0, 1, 1, 0. And so notice that there's a loop right there. So the path to get to there the first time, x, is 0, 0, this, 1, 0. And that's how we get there the first time. And then y is how we get back. We see 1, 0, 1, 0. And then z, which gets us to the end, is 1, 1, 0. 1, 1, 0. So now, from that string, we now have these three pieces, 0, 0, 1, 0, 1, 1, 0. And so notice that we can have x and then y any number of times, and then z, and it will always reach an accepting state. And that is kind of intuitive because z is 3 long, and so since z is 3 long, and this thing looks and sees if the third thing from the end is 1, and the third thing from the end of 1 right here is 1, we know that it's going to accept. So this process of looking at a string and finding out these pieces, you could like turn that into a function. In the assignments, I call this the pumper function, where it takes a trace and it pulls out what the individual pieces are. Okay, so we've now seen some examples of this regular pumping property. Now let's write it down formally. So we'll write down the formal definition of the regular pumping property. So the regular pumping property, or RPP. An RPP is a property that applies to some language. So it's something that is a relation between languages, which are elements of the power set of sigma star, and it's a proposition, so it goes to prop. Okay, so we'll say that RPP of A is equal to the following thing. First, since this is a property that applies to regular languages, that means that there exists some machine for it. And that machine has some size. So therefore, what we do is write down there exists some number p inside of the natural numbers. That number p, we know, is the size of the states. That's when we're doing a proof of RPP, where we're proving it on regular languages, this is when we say p is the number of states. Where for all s inside of A, such that the length of s is greater than or equal to p. Okay, so this says, now take the strings that are actually in the language that the DFA says yes to. Okay, so imagine they're the ones that say yes. Those ones that are greater than p, i.e. that are longer than the number of states, i.e. that visit every single state, that either visit every single state and have to repeat. Okay, there exists strings x, y, and z inside of sigma star such that s is equal to x, y, z. So we can divide up the string into those pieces. Next, there has to also be the case that the length of x and y is less than p. And what does this mean? This means that if you're going to get a repeat, you have to have the repeat before you get over the number of states. Because remember, the whole idea about getting a repeat is that, we'll see more and more states, and eventually we have to get a repeat. And so that has to happen before we've seen the number p. The number p states, which is, of course, the number of states in the machine. And then there's one more property, that the length of y has to be greater than 0. And why does it have to be greater than 0? It has to be greater than 0 because the loop has to actually be there. There has to actually be a loop where you start in some state and you visit some characters and you get back again. So if something has RPP, if there exists this number, where for all of these there exists these three things, and that means that for all I inside of the natural numbers, x circ yi circ z is inside of A. The regular pumping property is essentially a recipe for if the regular pumping property applies, you know that given one string that's long enough and accepted, you have a recipe for an infinite number of other strings. And it turns out that regular languages, they all are infinite in exactly this way. There's no other way that they can be infinite. So, we've now done the first two parts of our battle plan. We've figured out what is the property that every regular language has. Then we've shown that every regular language has that property. We kind of did these at the same time. I guess we kind of did one and then we wrote down 0. And then now what we need to do is we need to prove that it's not the case that some particular language has that property. And we'll do that next time.